getting a view of the samples today will help give you a sense of why we might size fraction. But just as a reminder, it reduces the particle load by separating the sample into more manageable portions, and it also creates bins for data analysis for the particles. Again, as you may have noticed today, it's easier to focus on more similarly sized particles so that you're not biasing your picking towards the large particles, and missing some particles is a little bit reduced if you've size fractioned. So on the left, these are the size fractions again that we're using for this study. So there is a bit of range in the sieve sizes because it depends on what you have access to in your lab, but we're going to ask that you use a 300 to 350 micron sieve as your largest size fraction, a 100 to 150 sieve as your second size fraction, and then probably 2 filters, because I don't think many people will have a 20 micron or a usable 1 micron sieve. So those are the other 2 size fractions. Another reason that we size fraction is if you are trying to do some form of automation, if you have large particles on your filter surface for the 20 micron or 1 micron size fractions, there's a pretty good chance that your large particles will obscure the small particles underneath them. We're trying to avoid that particle overlapping issue, so size fractioning helps reduce that.
Okay. So I'm going to go through the filtering SOP. It's the simplest one, it's the first and easiest one. So for the study, we're using this as the method for drinking water. So it'll just be clean water that you'll receive with the spiked particles in. There's almost no sample preparation. You just directly pour the sample into your sieve stack. So again, you have the 300 to 350, 100 to 150, and then you would have a sieve pan at the bottom to catch anything else that falls through. I'm going to be doing a demonstration of this later this afternoon, so I'll just briefly discuss what you do with the different size fractions. So the top one, the top 2 size fractions, you'll rinse the sieves with reverse osmosis water or whichever filtered water you choose to use. You'll rinse any particles that are caught in each of the sieves into a separate jar, and the jar should look similar to what you had earlier, but obviously there will be a size fraction rather than a varied size of particles. Then the content of the sieve pan, we'll filter. We use a vacuum pump in our lab, but I know people have different methods that they use for this. So you will take the sieve pan contents, filter it through a 20 micron filter material of your choice, and then whatever you catch in the bottom of the filtering flask, you'll then retain this and filter that again through a 1 micron filter. The waste in here is now waste, you don't need it anymore. You should have captured all your particles. So you'll end up with a 300 to 350 micron size fraction, a 100 to 150 micron size fraction, and then 2 filter papers. So the filtering process is pretty simple.
If you read through the SOPs, like we said, we like to do the wet picking, so we'll pick from the jar, but you don't have to do that. So it does give you the option to pick off of a filter if you want to pick off of a filter. If you're picking off of a filter, you may end up with 4 filters instead of 2 jars and 2 filters. Are there any questions about the filtering SOP before we move on to the next one?
Yes.
So if you decide to filter the larger fractionation classes, should they go onto the 20 micron filter? Is that what you recommend for this?
We're not telling you what type of filter
It's
to
just
use
whatever
or
we
what
decide
size.
to
It's whatever you decide to use, but we are asking that you still size fraction. So hopefully what will happen is even if you're using a 20 micron filter for your large size fraction, hopefully the particles that will be on it will still be from the right size fraction. So still put it through the same stack, but if you want to filter, you can filter on a 20 micron filter.
And if we have a 20 micron sieve,
Then you can put it in a jar. You can use a sieve there if you want to instead. And there's also going to be an augmentation study specifically for people who have a 20 micron sieve. So if you have a 20 micron sieve and you want to participate in that study, you can ask Steve or Charles for more details about what that study will be. But you don't have to.
Yeah.
I'm already participating in.
Oh, okay, good.
They're in.
Sorry.
Yeah. And then a lot of people don't have 20 micron sieves, which is why we said to use filter papers. So first off, just from first looks, does this method make sense to everybody? Cool. Any questions? Okay. We'll move on to density separation. So we won't spend time reading this. I'll just give you a brief overview, and then hopefully when you go to read it, it will make a lot more sense. So the density separation It's again pretty simple, but it's most commonly used. We're going to use it in this study for sediment samples. There's a method to extract microplastics from sediments. So the first step of this would be to prepare your calcium chloride solution. The details of that are in the SOP, and we'll go through that in more detail tomorrow. But then the actual step of the method would be to take your sample from your sample jar, put it into a beaker. We suggested I think a 500 milliliter beaker. You then add a volume of CaCl2. You stir this vigorously, not too vigorously, for 2 minutes. And then I'll leave out the details, but then you will cover this and leave it to sit for 2 hours to separate. Minimum of 2 hours, but around 2 hours. Once this has happened, you should see a clear floating layer and a clear sinking layer. I'll explain about the purpose of calcium chloride actually while I'm here. So, water has a density of 1 milligram per litre. We use a calcium chloride solution and we get it to a density of 1.4 milligrams per litre. The reason being is that this will allow anything that's less than that to float to the top. So plastics are around 1.2, some are above, some are less. But by having a solution with a density of 1.4, this means anything that's below that will float to the surface. You could do a density separation in an example with water, but it would take a very long time for these things to separate, and you might not get everything that's plastic that floats to the surface. So that's why we use calcium chloride, and it's much quicker when you use this. So back to the process. So once you have this floating layer and you'll have a sunk layer at the bottom, you'll then transfer the floating layer into beaker 2, which we're calling here, which would be a slightly larger beaker. So you transfer that into the beaker 2, you would then repeat another density separation in beaker 1. And the reason we've said to do this is because this ensures that any particles that might have been trapped under other particles for the original density separation have a second opportunity to float to the surface. So you repeat the same process with whatever's left in your first beaker. You'll add calcium chloride solution, stir it for 2 minutes, cover it, leave it for 2 hours. When you get your second floating layer, and you will get things that float in the second density separation, you'll transfer that into beaker 2, the same beaker that you used before. So you'll end up with 2 density separations in the same beaker being put into one, another larger beaker. This you then leave overnight to settle, so like 12 to 24 hours, and then the floating layer from that you will transfer again, but this time it will go through the size fractioning process. So you'll be spooning and decanting, which we'll show you tomorrow. Your floating layer straight into the sieve stack, and then you collect your sieve pan contents in the bottom. Your sieve pan contents will again, just as in the filtering method, it will be filtered through a 20 micron filter, and then again through a 1 micron filter. Does this make sense? Everyone, does anyone have any immediate questions about the density separation procedure?
So we're only doing the low density stuff.
Yeah. So we know not everything will float in this, and so we know that. We know the density of the solution. We know that it's not going to capture everything. And we know that there are other alternatives to use for density separation that may work better. The reason we've chosen calcium chloride is ease of access, how safe it is to work with, and how cheap it is. So some people prefer to use something like zinc chloride, some people would prefer to use sodium iodide. Some of those things work better or worse. If you use one of those things and you feel strongly about it, then you have the option of doing an augmentation study, which you can again contact Steve or Charles about, where you can test different solutions now that you have a nice set of prepared plastics ready to go to test this.
Yeah.
So for this study, if you're not doing an augmentation study, please use calcium chloride and follow the SOP. If you want to do another study on top of that, contact Steve or Charles.
Yeah. It's again the same reason why we've got 2 beakers rather than a separatory funnel. Yeah.
When you're doing the decanting, I always get worried that things are going to stick onto the
Yeah.
vessel. How do you deal with that?
We spoon the top floating layer into the second beaker.
Oh.
So you scoop the top layer, and then we gently rinse around the edge of the beaker, try not to disturb anything beneath. So you get everything that's possibly stuck to the sides in that process, and then we decant the rest of the liquid, and we stop at the point at which the bottom sediment starts to move. And because we do it twice, it should hopefully get everything.
Yeah.
Yeah.
There's a spike in recovery study that Jelena Gerbic did in our lab a while ago where she tested the recovery for these things, and we found so far that it works pretty well, but we'll have a much better idea of how this works after this study.
You guys love your scoopers.
Yep.
Yeah.
You guys love your
We
scoopers.
do, and these specific shapes and sizes of spoons are really useful.
Yeah. Ask Wayne where he got them from.
Yeah.
I have the number if you want that, so you can question it from
Yeah, because we use normal teaspoons, but I found sometimes I have to like bend the spoon to create like a ladle shape to make it easier. But these are actually really good, like a miniature soup spoon is like how I'd ideally have my spoon for the scooping procedure. But you'll see more of that tomorrow.
Any more questions for now about the density separation?
Yeah.
If you want to do the sediment density separation, how much sediment, the ratios between sediment and then the solution, should we worry about it?
Yeah, so it will be a set amount of sediment that's sent to you in your samples, and then for that we recommended a minimum amount of calcium chloride to add to the beaker. I think we've said about 300 mils. The reason being is because you don't want to have too small a volume in your beaker because, yeah, and also when you're scooping you can, the more volume of calcium chloride in the beaker, the clearer the separation and the less likely it is that when you're scooping and things like that, you're not going to disturb the bottom sediment. So we've said a minimum of 300 mils and we think that works fine from when we've tested it and used it.
So is there any chance that the sediment will be containing plastics after this process?
There's a chance because we're not telling everybody what's going into the pills. So
And
that's
some
supposed to be
plastics
important.
have a density greater than 1.4,
Yeah,
like PVC.
yeah, yeah. So we're assessing recovery given the solution. Whoever does the augmentation study or however many people participate in the augmentation study may get a different recovery if they're using a different solution for the density separation, which is useful information. But we can't tell you guys what's in the pills, and we also don't know what's in the pills because it's supposed to be a blind study, so we don't know the polymer types or the quantities of each one.
We're not going to be looking at the sediment.
No.
Oh, yeah, you mean the layer that's sunk?
We're not going to make an attempt to look at that and see if we see anything.
Unless that becomes part of the procedure for one of the augmentation studies.
Okay, but it's not for this
Not for
particular.
this
Yeah,
study.
in the standard study, no.
Okay, so we're going to move on to the next one. Okay, so this is the potassium hydroxide digestion. So this is the digestion that we're using for the fish tissue samples that we're giving you. This is, again, a general overview. There's more information and more specifics provided when we do the actual demonstration. But the general overview is that you'll take your fish tissue sample, which will be spiked with the plastic pills. You'll put it into a solution of 20% potassium hydroxide that you'll prepare and filter ahead of time. Then you'll incubate that at 45 degrees Celsius for 48 hours. Once that's been incubated, you can put it through the smallest sieve, so you don't need to use both sieves here, just the smaller size fraction, and then you'll catch whatever moves through the sieve in your sieve pan. The contents of the sieve will go into a 10% alcojet solution, so this is a detergent solution to break down the fatty layer, fatty residue. It's going to go back into the same container that you did your potassium hydroxide digestion in, because you may notice that there's like a cake layer around the edge of the container. So the detergent should break up the fat from what's in the sieve, but it should also break up the fat from what's stuck on the container itself. And then you'll take what went through this 10% alcojet detergent soak and put it through the full sieve stack this time. This is where your size fractioning comes into play. What's in the 300 to 350 micron sieve will go into a jar or a filter if you choose to do filter instead. Same for the 100 to 150 micron size fraction. Where it differs is the sieve pan. So now you'll take the sieve pan here and whatever you save from the sieve pan here and combine them together, because some particles may have been freed up by the detergent soak, and you'll filter those. First, it will be filtered onto a 20 micron filter. Then you'll take the filtrate that moved through, filter it again. This time we're adding in a 10 micron filter here. This is because these are really messy samples and they're really difficult to filter. This should make the filtering step easier. So you'll have a 10 micron filter here. And then you're going to take the filtrate again, heat it. We're going to heat it to around 50 degrees so that it's more liquidy, and try to put it through a 1 micron filter. So as you'll see tomorrow, this is not an easy process to do. especially as the solution with the fish tissue in it cools, it gets like chunky and fatty. That's the reason we're adding in this extra filtering step here. I'll demonstrate this tomorrow. As we try to put it through the filter, there's some detergent, warm detergent involved in this process as well, which should help it move through the filter. Doesn't work that well right now. It's a challenging and tricky process, so what might end up happening is you may have multiple filters for your smallest size fraction if you clog your filter. So you could have smallest size fraction part 1, part 2, and so on. That's another thing that we're testing. If we come up with a way to improve this SOP over the next month, everyone will know. We'll modify the SOP and inform you if we've modified it. Yeah.
Have you tried SDS instead of Alcojet?
Yeah, and it doesn't, so we still have issues with the SDS as well. So that's why we've stuck with Alcojet, because that's the one we're using in the other procedure, so you'll already have Alcojet on hand. We've also tried Contrad, which is another type of detergent, but that one gets really foamy, so that creates issues as well. But if you have any suggestions, something that you think could improve this SOP for the 1 micron size fraction, feel free to let us know, because if we can test it over the next month, again, we'll modify the SOP and let you know. And if you wanted to design an augmentation study where you're testing different types of detergents or something like that, that's something you can also propose. Any questions about the potassium hydroxide?
How slow do you consider the dripping to be before you consider the filter to be clogged?
So what we'll show you tomorrow is if we'll only put tiny volumes of the liquid in at a time, and you may have like a 4-liter beaker full of solution to put through that 1 micron filter, could happen. We'll only put 150-ish milliliters in at a time, and we're heating it as we go. And then once you notice that it's not moving down any further, you can add some warm detergent to help it move through. If it doesn't move at all, you can take that, pour it back into your beaker where your stored solution is, change the filter out, and start again. It's not ideal, but it works. It just takes multiple filters. If we have a way to improve it, we will improve it. You keep everything covered at each stage of the process too, so even while you're filtering, you'll have aluminum foil covering the filter cup, so that should mitigate the contamination issues. Any more
Do you
questions?
settle on KOH as the reagent because it's the most effective, or is it also optimized in terms of like your previous steps in terms of accessibility and
Yeah.
cost?
And like how dangerous it is to work with. So, and it's because it's one that's commonly used in literature, it's one we want to evaluate in this study because that tends to be the one people go for. But we are also doing wet peroxide oxidation just for a different matrix. And if you wanted to do something where you're assessing enzymatic digestion or something like that, then that's again an augmentation study you can propose. But it's complicated, tends to be a little on the messier side, and can be costly. So we haven't used it for this study. Doesn't mean that we don't think it's a good method. Okay. Any more questions? Yeah.
Yeah, I have another idea. Maybe for the 1 micron one, if you dilute the Alcojet by a lot.
We
tried
tried
that.
diluting
Good.
both the Alcojet and the filter, and it still wouldn't.
Okay.
Yeah.
You're 2 steps
Yeah.
ahead of me.
This is like, bear in mind that this is like 2 months of extensive testing for these
Yeah.
SOPs. So we've tried a lot of things and we've come up with a solution that is possible. Doesn't mean that it's necessarily the best, but it is doable. Like we said, what we expect to happen is for this final filter, you'll probably have the sample spread over multiple filters. The other ones move through well.
Have you tried to do like a digestion at the end before the final filter?
We haven't added in a second digestion. So we're trying to keep the SOP simple as well, but that is something we could try. But I would say if we are trying, that's probably more likely to be an augmentation study than the actual study. Also, a lot of people aren't going to be going down to this size fraction either. So there's only going to be a few of us that are actually trying to do this with potassium hydroxide. Okay. Any more questions with the potassium hydroxide? Okay.
And you haven't had problems with the 20 micron filter? That's
No,
gone
the
through really nicely.
20 and the 10 move through really well. Yeah, it's just the 1 micron.
It's a lot of effort to
But
get down to that.
it is, but we don't want to drop it out because that's the size range that so many of us are really interested in learning about.
Yeah.
So, yeah, in my own work, I don't go down to 1 micron. I have no issues with the potassium hydroxide. But for the study, we are really trying to keep it in. Okay, so again, we're demonstrating all this tomorrow, so you'll see it in practice as we go through. This, believe it or not, is the simplified overview of the wet peroxide oxidation. So this is what it's also called Fenton's reagent. So this is what we're using for what we are calling a dirty water sample. So this is our dirty water sample here. What you're going to do is put it through the sieve stack. So you'll notice this time it's just 2 sieves. I don't have the sieve pan at the bottom here. It's because we're not trying to go down to the smallest size fraction for this one. We're stopping at the 100 to 150 micron size range. We tested it, and it's not really feasible to try and go down to the 1 micron size range for this one. For the potassium hydroxide, we were able to make it work. For this one, it's not really feasible. So you just have your 2 sieves. You're only capturing what's in the sieves. For the top sieve and the bottom sieve, you're going to put each of them into a beaker. In each beaker, you're going to add 20 mils of the iron sulfate solution and then 5 hits of 20 mils of the hydrogen peroxide. After your 5 hits, you'll sieve. For the top one, you have to put it through both sieves in case smaller particles were freed up during the digestion process. For the smaller size fraction, you just have to put it through the smaller size fraction because we're assuming the larger particles were captured the first time. If it needs another round of digestion, you can put it back into the beakers and do another round of digestion. You can do as many rounds of digestion as you need, and you can record how many rounds of digestion you've done. Once you feel like you've gotten it to a place where the organic content is gone or it's not going anywhere, it's not getting any smaller regardless of how many rounds you've done, you can stop. When you stop, you'll put it back into the original beaker, the same beaker as over here. The reason you're putting it back into the original beaker is the same as it was for the potassium hydroxide digestion. There may be some fatty layers or oiliness caked onto the side of the beaker that you want to capture. When you have it in the beakers, you're going to add your 10% alcojet again, and you're going to let it sit overnight, so 12 to 24 hours to break down any fatty material that's left over. After the digestion step, you'll sieve again. All these sieving steps are why we're not going to ask you to try and capture the sieve pan from each round because you probably end up with like 10 liters of liquid here. When you're doing this, each time this top beaker has to go through both sieves in case particles are freed up in this process. If you get any particles, or whatever you get in this sieve, you'll recombine at each step, and here you'll rinse into jars. So this top sieve will go into 1 jar or 1 filter. This bottom sieve and the bottom sieve from the second beaker will be combined into either a jar or a filter for counting. So this time, you're only going to end up with 2 end products, so 2 jars or 2 filters. Any questions about the wet peroxide oxidation?
And that's a heated application of Fenton's reagent.
It is, but we'll demonstrate this tomorrow. It is heated, but you have to be really careful about the temperature that you're using for both safety purposes and to not lose your particles. So you'll see when I do this, I babysit the samples the whole time. So I'll sit in front of the fume hood and I'll have thermometers in the beakers the entire time and watch the temperature. We've made the cutoff, the absolute cutoff for temperature to be 55 degrees, but because this is kind of dangerous and reactive and it overflows really quickly, I actually recommend trying to maintain a lower temperature. So I say somewhere between 45 to 50 degrees. Once it hits that 60-degree mark, it spikes very fast. It's way too hard to try and bring back down. So absolute max of 55, but please try to keep it lower than that for safety and for the sake of your particles. Any other questions? Yes.
What kind of dirty water can you use for this method?
We're providing that to you. So we're gonna, for this study, we're giving you the sample to spike with plastics. So you don't have to worry about like adding stuff in to make it dirty. It's already gonna be done.
And do you knock down the bubbles with a fast stream?
You can use ethanol if you want to bring down the bubbles, because I also just use water. Water tends to work pretty well too. So if there's bubbles from the detergent, and Alkazet's a low foaming detergent, so it shouldn't be much of a bubbling issue with the Alkajet, but you can use ethanol to bring down the bubbles there. I just use RO water in a squirt bottle while I'm doing this to bring down the foam. Every sample behaves a little bit differently, so we'll see what the samples are like when I do the demos tomorrow, but sometimes you'll see that it foams, and the foam can rise pretty quickly as well, which is why I'd like to ask you to babysit your samples and just sit and watch them in front of the fume hood. I know it's a little bit boring, but if they do start to overflow, you want to bring them down as quickly as possible. It's also nice to try and avoid having the samples caked to the side of the beakers well above the line where the liquid is. Any other questions?
She has one.
Yeah, I'm sorry, I'm not clear as to the 10% Alkajet. What is it for?
It's a
That
detergent.
it's still-
Yeah, so
at least point.
The 10% alcojet is what we use to break down oily or fatty residues. So for different samples, you'll get like a crustiness or a fat layer, an oil sheen on the top of the samples. The plastic particles are buoyant, they float, and they get trapped in this fatty layer. So the detergent helps break that down. Okay. So the wet peroxide. Pardon?
I get it for the fish, but samples are.
So there.
Or
So
tissue,
I'm not sure
but-
how much detail we're allowed to give you about what's exactly in these
okay.
dirty water samples,
Yeah.
but we're looking at dirty water samples as if it was a surface water sample or a groundwater sample. So if it were a surface water sample like a manta trawl, logically you may expect things like algae to be contained in that sample as well. I don't know if I'm allowed to say any more than that, so I'll stop there.
Spoiler alert.
But
This
it's-
is
yeah.
what we do for particle size distribution
Yeah.
analysis.
Okay.
So in screening, fibers are longer than they are thick, and a long fiber can go through
Yeah.
a very fine sieve on occasion.
Yeah.
But your determination is the longest length.
Yeah.
So you're not just gonna accept the fact that it went into the 100 millimeter sieve as being a 100 millimeter particle.
Down. Yeah. So we use the sieves to create size bins, so that's a good way to start with separating the size classes, but we know not every single particle that ends up in the sieve is going to be in the right size fraction. That's why we're also asking you to take pictures and measure a subset of your particles. It's 10 of each color morphology combination, so that would be like 10 of every blue fiber, 10 of every white fiber, and so on from each size fraction. So it will end up being like a fairly large number of particles, and in some cases you may pick all of the particles out if there's fewer than 10 of each of these color morphology combinations. You're measuring those particles, so you'll know the size of the particles that you've measured. So we'll be able to see if things are winding up in the wrong size bins created by the sieves. We may not know every single particle if there's more than 10 of each color morphology combination, but we'll get a really good sense of what's there. But that is a good point. Any other questions? Yes.
So it seems like I understand why you guys have picked the 10 items of morphology and color. But it seems like for us, it might make sense to do more than 10, right? So we can do some kind of rarefaction to see is 10 the right number. So not maybe everybody do every single sample because that would take a lot
Yeah.
more time, but maybe the first and last or something, people do like 20 or something.
So there's a subset of people that are going to be asked to do every single particle. So that one will be a lot more work, and I think the plan is to split that out so not one group is doing every single particle
Okay.
for every single
Okay.
extraction method, but that is going to be covered. So we should have an idea of the some sample groups and then an idea of some people who've done everything.
Okay.
Okay. Any more questions? Okay, so we're going to go through each of these as demonstrations tomorrow. So you'll see them happen in person, but not in real time. So we don't have enough time to go through everything tomorrow, so we'll have demonstrations prepared for different stages. Parts of it we'll do in person all together tomorrow. Other parts we just have examples to demonstrate. But if you have more questions when you read through the SOPs tonight, have them ready to go. And then if you don't get around to asking the questions in person tomorrow, then send Hannah an email and we can both go through them. Okay.
Shall we have a little break and then we can do
Yeah, let's have a
a drink
break.
demonstration?
Yeah.
Okay, so if anyone wants to go